So when we look at one curved mirror, what we're really doing is just looking at half of a lens. And what a lens is a piece of glass or really any other transparent substance. So sometimes it's a pretty clear or sanded down piece of plastic that has curved sides. So we should insert with curved sides here for dispersing light rays so that the image can, in most cases, be magnified. So we can think about this as eyeglasses or even telescopes. Right? So again, I want to emphasize on the fact that they should have curved sides, whether it's a concave lens or a convex lens. So to make sure that images are proper, we must make sure that the lens is thin. So lenses refract light in a way which spreads light out, or we could say it diverges, so a diverging lens, or it'll concentrate or focus light at a point which would be considered a converging lens. So converging lenses are always convex in shape. So if you look at a converging lens over here in the diagram, you can see that it is essentially two halves or two convex mirrors that are binded to one. And what that means is if you look towards the center over here, we could say that the center is thicker, right, than the edges, and the edges would really refer to the top and the bottom over here. And what that means is that it'll concentrate light at a certain point inside that lens. Now, diverging lenses, or lenses that tend to spread light out, are always concave in shape. And so if we look at this lens here and we split it down the middle, we could see that there are essentially two concave mirrors that are bounded to form one lens. Or this is sometimes called a double concave. And what we could see here is that the edges, so the top and the bottom, the edges, unlike the converging lenses of the double convex lenses, the edges are, you could say, thicker, right, or larger than the center. So they work opposite to the converging lens, and they're going to refract light differently as a result. So just like in mirrors, we need a principal axis, which is this line over here. That becomes a reference point for the object and the image that is produced of the object. But when it comes to lenses more specifically, we need what we call a principal plane, which is a line that cuts in the center like that, in between the two halves of the lens. And the idea is that they would essentially be two, in this case, concave mirrors that have joined together to make a lens. And so you'd have a line through the horizontal half, that's the principal axis, and then a line through the vertical half, which is the principal plane. More specifically, the principal plane is going to be where the light is going to refract. So once it reaches this plane here, you should see light bend a certain way. Like mirrors, we still draw a focal length, but we're going to do it on both sides. Since light is going to refract on one side, there isn't going to be a center of curvature. So we're going to put a no center of curvature. And the reason being is that because the lens itself is a complete circle. So there's no real center of curvature. What we do have, though, and I'll signify this in a different color, we have the center of the lens, which occurs when both the principal plane and the principal axis meet. So we're going to call this the center of the lens. And lastly, both converging and diverging lenses apply the same ray rules. I've made a kind of converging lens over here, but really I could have used any of the lenses, diverging or double concave, etc., in order to show where the focal lengths go in the center of lens. So what we're going to do is we're just going to use a converging lens in order to demonstrate the 3 ray rules. So the first rule states that any ray shot through the focus will refract parallel to the principal axis. So let's say I drew an incident ray that goes through the focus over here. And let me angle that a little bit better. So let's say something like that. Okay. And here is the incident ray. I'm going to change the height of the object so that it's a little bit more realistic. Okay, so the point where it hits the principal plane right over here, it is going to refract. So it's going to bend parallel to the principal axis. So it'll be a straight line that goes like this, and it's going to bend in behind the mirror. And this is our refracted line. A refracted ray, we can say. Okay, the second rule states that an incident ray parallel to the principal axis, to the blue line over there, will refract so that it passes through the focus on the other side. So let's say I start on the top of my object and I draw an incident ray that is parallel. So remember that as soon as it reaches the principal plane, it's going to refract. So here it is. Here's our ray. Now what it's going to do is it's going to refract through the focal point, not on the left side, but through the right side, like so. And so these are the differences between the first and second rules. However, both of them refract on the opposite side of the mirror. Now remember, you need at least 2 lines or an intersecting point in behind the mirror to form an image. So what I would do is I would extend each of these refracted lines until they intersect, which would be over here. And like our previous mirror diagrams, this is where your image would form. The last and final rule says that any ray that passes through the center of the lens, so that's that yellow spot in the middle, will come back the way it came and will not refract. So if I, from the top of the object again, if I send it through as follows, it will simply go this way from the object, but then just return the opposite way where the image would be formed at those intersecting points. So in this case, there would be no refraction. You would just see not a bent line at all, just simply a light ray going through the material or the object. So these are the 3 rules exercise. Now, if I'm going to draw the object, and let's say I'm going to draw the image, I should say, not the object, but the image. Let's draw that in kind of a maroon-ish color. Since all the incident rays start at the top, then where they all intersect over here is where I would draw the top of the object and then extend it over here. And I would see that my object is inverted. It also forms, if we compare the two, an enlarged image as well. So the image over here is significantly bigger than the object. So we're going to write enlarged as well. And so these, when it comes to a converging lens, it'll always be producing an image that is enlarged and inverted. Lastly, we're going to say that when an image shows up on the other side, it's a real image. And while that might be counterintuitive when we think about the mirror diagrams, The explanation is quite simple. Why? Because when you actually shine the light through through a lens, specifically a converging lens, the image really does go through the lens, right? And onto the other side. And so because in real life that's exactly where you would see the image formed, through the lens and onto the other side, it is a real image. So a converging lens is always going to form a real image, although it will be inverted and enlarged. So just for thoroughness, we're going to show you an example of the divergent lens. Now, all the rules that we listed before for the converging lens are going to be the same, except the refracted rays will be on the same side as the object and not on the opposite side of the mirror. But all the rules are going to really remain or be applied. It's just going to look a little different in the end in terms of where the image is formed. So what we're going to do is when we're drawing these ray diagrams, we're going to show you what you would really see versus where the image is actually formed. And with all that combined, we're going to determine whether this is a real or virtual image. So let's say that I take from the top of my object and I draw an incident ray that is parallel to the principal axis. So remember that the principal axis is in blue and the principal plane is in red. So here is the incident ray that is parallel to the principal axis. Now what it's going to do is it's going to refract, okay, towards, or through, I should say, the focal length. Now we're going to make it refract going this way. Now what you would actually see is, and remember I would actually extend this all the way to the principal plane over here, the incident ray, but what I would actually see is that refracted line would then extend at the same angle that it went through the focal point through the other side, and you'd see a line like that. Now I'm going to redraw that dotted line so you could see it a bit clearer. So now that I've straightened this line out, that dotted line would be the sort of ideal, we could say refracting line, but the solid line would be the one that you would actually see in real life. So this is the real refracted line. And so again, though, I would extend the dotted line through the focal point on this side. Now, to better understand how this works, we're going to do another refracted ray. This time I'll do it in red. Let's say I took my ray diagram here, or my object, and I shot an incident ray through the center of the lens. Well, according to our previous diagrams, if I did that, it would just be reflected back through the center of the lens. And so my refracted ray, I should say, if I'm going to draw the arrows in red, my refracted ray is going to go back this way. Right, so it goes back the way it came, and then it doesn't really refract, right? You wouldn't see light bending, you would just see a light going through the object. Now, where do they intersect? Well, they intersect right over here, the missing line, and I'll draw it again here with the highlighter. They intersect right over here. And so that is where the image is going to be formed. Now, since the incident rays are taken from the top of the arrow, where the lines intersect, I'm going to make it the top of the arrow. And then, of course, it wouldn't go past the principal axis. It doesn't go underneath the mirror. And so we can see a couple of things. First, that the image, if I'm looking at the image that I'm going to highlight in yellow over here, the image is upright. It's not inverted. Second thing is that if you're comparing the two sizes, the image is smaller. And it's significantly smaller. Lastly, if I'm looking at whether it's real or virtual, well, in real life, what you would see, and when you do this in the lab with your teachers, you would see these lines over here going through the object. What you wouldn't see is the image being produced over here. So because it's not really in front of the mirror or on the side of the object, it is a virtual image. So it actually switches rules when we're comparing them to mirrors. And so to sum this up, we can say the following when it comes to lens versus mirror. We can say that for converging lenses, they'll always create real images despite being in behind the mirror. For diverging lenses, which means they use concave mirrors, they're always going to create virtual images despite being in front of the mirror. And that's because the image formed or that you'd see in the real world are not actually there. Moreover, converging lenses would have a positive focal length, right, which is given as the variable f. So I'll just write focal length here. And then diverging lenses would have a negative focal length, despite us using the focal length in front of the mirror or on the same side as the object. And so if you can remember these key little rules, a lot of the problems that you're going to attempt really just repeat themselves, and it's really going to help you isolating these key special notes.